Okay, we're going to record the second part of the model answers to October 2021 Physics Edexcel International A-Level exam for Unit 2, Waves and Electricity. We went through questions 1 to 12, which included the multiple choice in the previous video, and this is the second video to complete this paper. Okay, so we got up to question 12. Question 13 is the first one that we're going to do now. And unfortunately, I recorded this once and I had to delete it because of a technical issue. So I'm going to go through it again. So that's why I've got a lot of the red parts for what I did in the last video. So it says a filament lamp is marked voltage of 12 volts, power of 60 watts, and the filament lamp is made of a long metal wire with a diameter D of 0.25 millimeters. The metal has a resistivity of 5.6 times 10 to the minus 8 ohm meters, and when the wire is at a normal operating temperature. That's a controlled variable. So this is important when you are doing Unit 3 exam, that you're aware why it's important to keep the temperature under control. So in the core practical will be you'd have a switch and only keep the circuit on connected while you're taking readings. So I like to put all the letters in to show you where they come from. So the first equation, they want you to calculate the length in the equation from resistivity. We know rho is given to us. We know area can be calculated from the diameter. If you calculate, I actually did the area as part of it. So I did it all algebraically, but the area is from here is in this equation is pi d squared over 4. So if you just calculate pi d squared over 4, it comes to the number here, and you'll get a mark for just doing it in bits. What I've done is I've actually converted the two equations, which is the resistivity equation with the power equation, given the information here about the power and the voltage. So if we know the power and the voltage, we know power is V squared over R, we can work out resistance is V squared over R. So likewise, if you do the area, you get 1 mark. If you work out the resistance from V squared over P, you get 2.4 ohms. What I've done is I'm showing you algebraically that you can replace R here with V squared over P. So all I've done is written, well, V squared over P instead of R. I've changed the subject of the formula to make L the only unknown, because we know R from V squared over P. There's R. So I've changed the subject formula to make it R. This is R. A, we calculated already. Resistivity we're given. So if we do V squared over P instead of R, multiply by the A, which we've got already calculated, divided by the value given for resistivity, you can do it all in one go. So that's what I'm showing you, that you can work out the length is equal to this, multiplied by A over rho, which we already have done. So when you put all the numbers in, if you've put the values in already, we've worked out that the area is 4.9 times 10 to the minus 8. And we divide it by the resistivity, and we calculate the resistance is 2.4 ohms. You will come up with a length of 2.1 meters. So I'm just showing you that you can actually do it all in one go. Okay, but most students will probably want to do the area first, the resistance second, and then put it all into that equation. Okay, that's question 13. The first part of question 13 is done. The second part is putting these into a circuit. Okay, and this time the student has 2 filament lamps. Resistor A, which is the one that we've just been speaking about. Lamp A is marked 12 volts and 60 watts, and lamp B is marked 12 volts and 30 watts. That means that these bulbs are meant to operate at 12 volts, and if they do, that's the power that you'll get. However, the student sets up the circuit as shown. If you set up the circuit as shown in series, they're not going to get half the 24 volts each, and this is what the question is about. So the student states that both lamps will operate normally. Well, we already know from what I've just said that they will not operate normally, because you can't guarantee they're going to get 12 volts each, because the resistance of each is going to be different. As you know, you can work out using R equals V squared over P, yeah? what the resistance would be if they were operating at normal under normal conditions, which is 12 volts. So if you do that, the first resistor, which we worked out before, was 2.4 ohms. The second resistor, you do the same. It's 30 watts only. It shows that it has a resistance of 4.8 ohms at the correct operating temperature. So you know the resistances are different. Resistor A is much less than resistor B. So that means if you put a voltmeter across resistor A and you put a voltmeter across resistor B, they are not going to record the 24 volts divided equally between them. Yeah, the one with the higher resistor, which is B, will get more of the 24 volts. So because of that, the voltage across A will be less than the voltage across B, and therefore 24 volts will not be shared equally. So they will not, the voltage across A will be less than 12 volts, and voltage across B will be greater than 12 volts. So neither will operate normally. Now you can do some different ways to answer this question, but that's how I've done it. And if you look at the mark scheme, which you can download, you could work out the total current, which is the total voltage divided by resistance, and you'll be able to work it out. I'm not going to do it here because this solution is one of the accepted ones. And if you want to look at alternative ways to get a better understanding of how you can analyze such circuits, feel free to download the syllabus and take a look at it. Okay, the mark scheme, I mean. Okay, question 14 is about a gold leaf electroscope, which I showed my students recently. So this is the gold leaf electroscope. It has a gold leaf, which is a thin foil, which is stuck to a stem, metal stem, and at the top they put a zinc plate. Okay, it's used to demonstrate the photoelectric effect. So this question is about the concept of the photoelectric effect. When the zinc plate of the electroscope, so the zinc plate's on the top, is given a negative charge, the conducting rod and the gold leaf also become negatively charged. So basically, if this becomes negative, all the negative charges, because it's a conductor all the way down there, gold's the conductor, this is probably made of steel, it will all become negative, and the negative charges will spread out over that area, and the gold leaf will be deflected away from the metal stem because they're both negative, and repulsion occurs. So this creates a repulsion force which lifts or deflects the gold leaf away from the metal stem. So that's what it's telling you in the rest of the question. The deflection of the gold leaf depends on the amount of charge on the zinc plate and the conducting rod. Okay, so there is the question, the scenario, and then it says a beam of ultraviolet radiation is incident on the zinc plate. So I've represented the ultraviolet with a purple pen here, the photons coming in. The gold leaf immediately begins to fall back to the conducting rod. So when it's immediate, there's a quantum effect. And quantum comes in packages or certain sizes, quanta, yeah? So when you have the photoelectric effect, the photons are coming in, as shown here by this arrow with a wave on it. And when they come in, they give up all their energy to the electrons. And by doing that, yeah, it's an immediate effect. And it wants you to explain why this observation cannot be explained by the wave model of electromagnetic radiation. Well, if it's the wave model, in the wave model, energy is built up gradually over time, and it's basically a constant flow of waves, and therefore it's not the same as the quantum effect. So the electrons would not be released immediately if there was taken some time. But in the quantum effect, the photon comes in immediately, the electron absorbs all of the packet of energy, and if that one electron will immediately have enough energy to escape, and therefore gradually electrons will escape in this way if the photons keep coming in. So each photon must have enough energy to allow the electrons to escape from the surface of the zinc. If that happens, gradually the electrons will all escape and the object will become neutral. So electrons would not be released immediately if they were using the wave energy. In the photon model, the photon energy all goes to one electron straight away. Okay, one photon, one electron. So the buildup of the electrons escaping will be based on the number of photons that come in, rather than a gradual buildup of energy that comes in. Okay, so that's the first part of question 14. Question 14 continues. So as I explained, I think in a previous video, or have explained to you before, that when you're doing these questions, first you have to understand the concept, and then they'll use the mathematics. Okay, so the concept is the photoelectric effect, which means the energy comes in packages. The package size is E equals HF, and in this case, these ultraviolet photons, the radiation coming in, each have an energy of 9.3 times 10 to the minus 19 joules, which corresponds to a specific frequency. Okay, H is Planck's constant, and these are directed towards the zinc plate. So it wants you to calculate the maximum speed, which will be the maximum kinetic energy, with which the electrons are released from the plate. Okay, so basically what's happening? The electrons are below the surface. So in the question, not all the electrons are on the surface. The ones on the surface obviously is easier for them to escape than the ones which are maybe deeper inside the metal. So any electron that gets the energy from the photon, if it has enough energy to get to the surface and then have some spare energy, it will escape. So the minimum energy required is given to you by what's called the work function. Okay, so the work function for zinc is given to you as 4.3 electron volts. Now remember, over here they're giving us the energy of photon in joules, and here they're giving you electron energy, the work function in electron volts. An electron volt is the amount of kinetic energy that an electron would gain if given that voltage. And to work it out, you basically multiply the voltage, which is 4.3, by the charge of the electron, which is 1.6 times 10 to the minus 19. It comes from the equation E equals QV, which defines the volt, actually. So you have the charge is due to the electron, and the voltage is the size of the energy units in electron volts. So if it's 4.3 multiplied by the charge of the electron, you get how many joules that you require to escape. So you'll notice the energy required, the minimum energy required to get to the surface, that basically is called the work function of the metal, is less than the energy of the incoming photons. You'll see that's 9.3 times 10 to the minus 19 joules, and this is 6.9, so we have spare energy. So the incoming energy is this. The minimum energy required to be able to get to the surface is 4.3 electron volts, which in joules is this, and therefore the rest of it will go into kinetic energy. So if you subtract the incoming energy from the minimum energy required to get to the surface, you basically take away from this number this amount, and you're left with 2.4 times 10 to the minus 19 joules for the kinetic energy. So if you then change the equation to V squared and then cross out the square, square root it, you put twice the energy in there divided by the mass of the electron, and you can get straight to the answer if you do it all in one step. Okay? The mark scheme is looking for two significant figures here, because you'll notice all the data is given to two significant figures. Okay, so you should only quote it to two significant figures. So this is the photoelectric equation that you need to be familiar with, and it's given to you in the exam sheet. A student then suggests that a greater maximum speed of electrons could have been achieved if the following conditions are both correct. So a metal with a lower work function than zinc was used. Well, that's correct, because if the work function of this other metal is less than the work function of zinc, it means the minimum energy required to get to the surface of the metal is less than it would be for zinc. That means there's more excess energy left, which will go to kinetic energy. Okay, so this will the excess energy, of the HF, F times H, I should have written it the other way, will go to kinetic energy. Okay, so this would be true. So this is true. The second one, it says ultraviolet radiation with a greater wavelength was used. If it's greater wavelength, that means the frequency is smaller. And if you remember that the energy is related directly to the frequency and not the wavelength. So by making the wavelength greater wavelength means smaller frequency, which means smaller energy. So you've got to be able to put that into words. And this is how I've done it. So you have to drive the point home. So the first suggestion is correct because, as I've explained, and put it into words. So you basically got to do what I've done and be able to put it into clear English. 1 mark for the first suggestion, 2 marks for the second, because the second suggestion is incorrect, but the greater wavelength means that the photon energy will be decreased. So because of this. So you need to write in full sentences. Therefore, less energy would be available for kinetic energy of the released electrons. Okay? So remember, the energy released by photons, it depends on frequency and not wavelength. And they're just trying to see that you understood that. The next question. is question 15. They want you to derive the formula for resistors in parallel. So two resistors are put in parallel. I've drawn in a circuit, and you have to derive the formula for the total resistance of the two resistors. So we know that the total voltage of the supply is equal to the voltage across each resistor because they're in parallel. Okay, so this is one of the equations. You also know at the junction here, the total current coming from the cell will split into path 1 and path 2. So I total will be equal to I in path 1 plus I in path 2. Okay, so now we can replace IT, the total, by the total voltage by the total resistance, which we want to find out. And then you can divide voltage 1 by the resistance 1, add it to voltage 2. So basically you're replacing I1 with V1 over R1, I2 with V2 over R2. And since all the voltages are equal, you can cancel them out. So therefore, you're removing the voltage from the top of the equation. So you're dividing everything by V. It becomes 1 over RT equals 1 over R1 plus 1 over R2, as you know. So this is how you derive it. And you could do this for any number resistor, so it would be true. So any resistor you add into the path will decrease the total resistance because it's 1 over. Okay? So we'll go into that part of this concept in the second question, where they've given you the following situation. The diagram shows a combination of 5 resistors M, N, O, P, and Q as shown. Each one has a resistor of 5 ohms, 5.0 ohms to be precise. So we're looking for two significant figures in your answers. So first of all, I've done the inner circle here, N, P, and Q. So N is in parallel with P and Q. P and Q are 10 ohms because they're resistors in series. So you've got 10 ohms in parallel with N, which is 5 ohms. So the total resistance using our equation is 1 over 5 plus 1 over 10. So that gives you a fraction of 1 over RT equals 3 over 10, which gives you a value of 3.3 recurring. So that's 1 mark. Then I've done NPQ, the parallel of these NPQ, add it to 5 ohms in series. So you just basically got to add the 5 ohms to the O with the 3.3 that we worked out for the combination NPQ, gives you a total of 8.3 ohms for O in series with NPQ combination. Okay, then finally the 5 ohms of M is in parallel with the total that we just worked out, which is 8.3 ohms. So you can again use the same equation. This time 1 over 5 is the fraction for the M, and 1 over 8.3 is the rest of this combination. You add them up together. Ignore this is for the next part, which will give you a total of 3.1 ohms. So basically, by having resistors in parallel, it decreases it from all their individual resistors. And the way you can think of it is because you have more paths where the current can flow through, the more resistors you have in parallel. Okay, so the total resistance of the combination is 3.1 ohm as calculated here, which is approximately about 3 ohms. So try to make sure you do this in the exam. You say it's equal to 3.1 ohm, which is about 3 ohms as the question has asked. Okay, so look at this. I've just done another equation here, which we're going to go through in the next part. Okay. The student is told to modify the combination, it says. Excuse me while I just bring it down. A student is told to modify the combination of resistors that we just looked at. So the combined resistors between the A and B is now greater than 5 ohms. Remember, each of them was 5.0 ohms. She cannot change the arrangement of the resistors, so they're in the same positions, but she can replace one of the 5 ohm resistors with a 20 ohm resistor. So as you know, if you have any parallel paths, it will be less than the individual one. So explain without further calculations which of the 5 resistors should be replaced. Well, you have to replace resistor M, because if you don't replace resistor M, it stays at 5 ohms. And if it stays at 5 ohms, whatever you replace here, you're just adding another path in effect in parallel with M. Doesn't matter what the combination is. If you have more than one path, it means you're reducing the total resistance from 5 ohms. So the only way you can make it higher than 5 ohms is by changing M. Okay? Hope that makes sense to you. So once you do that, you know that M must be the one that you change, and then you have to put down what I've explained into words. So I've put replacing any other resistor in circuit would not create a higher resistance than 5.0 ohms, as the resistance of any parallel combination is always less than a single resistor's resistance. Okay, so this is basically what they want you to understand, that adding things in parallel reduces the resistance. Okay, the next question is question 16. And question 16 is about a hydrogen atom which has been exposed to suitable electromagnetic radiation. The atom can then emit visible light. Okay, so in this case, what's happening is by exposing it to suitable electromagnetic radiation, excitation will occur. And then any exciters, the electrons are basically in the atom, can jump up a level by the energy that's come in. Once the energy is correct, the excitation occurs. Eventually, these electrons will move back down, just like anything that goes up must eventually come down according to the law of physics, the laws of physics. The base, if you throw a pen, it's going to come back down again. So we'll try to move down to lower energy states whenever we can, and that process is called de-excitation. So the electrons will get excited by the incoming energy and then de-excited, and that process of de-excitation of the electrons leads to a photon being released each time. So every electron that de-excites produces a photon, and that is why the atom can emit visible light. The emitted light contains a small number of different wavelengths of visible light. So it's a hydrogen atom, so they're talking about an emission spectrum. Okay, so this is talking about an emission spectrum, and hydrogen only produces certain wavelengths that are corresponding to the energy differences that the de-excitation can occur in. So this is a 6-mark question, so whenever they have an asterisk, they're looking for the quality of your written communication and your ability to communicate your idea and your logically and in a reasoned fashion. Explain the process, it says, that results in the emission spectrum of different wavelengths of visible light from the hydrogen atom. Your answer should include reference to energy levels in atoms generally. So all atoms contain various energy levels. Hydrogen atoms contain the fewest. So that's just the underlying, you haven't got a mark yet. Electrons can move to higher energy levels, okay, when they absorb energy, obviously. So that's 1 mark. As long as you make the point that electrons can move to higher energy levels when they absorb energy. It doesn't have to be photon energy. It can be any form of energy. As long as they get the right amount of energy to jump up a level. Here are the levels in that I've drawn before. So they jump up 1 level or 2 levels or 3 levels. When they jump up, they are creating excited states. Okay. When these energy levels are discrete, that means they are fixed values that we have. They are discrete values, known values. The atom is said to be in an excited state when they have got the ability to jump up a level. Okay. Eventually, the electrons then drop down levels, and de-excitation is what this is called. This releases energy as photons, and this is the emission spectrum that will be produced by the atom that we're looking at. Okay. In hydrogen atoms, there are only a certain number of possible energy level transitions, I call it, and therefore that's due to the energy differences that you could have. So you can go from the 3rd level to the 1st, from the 2nd level to the 1st, and so on, and from the 4th level to the 1st. Or you can go from 4th to 3rd, 4th to 2nd, 3rd to 2nd, and so on. You get the idea. Each time an electron drops down a level, drops to a lower level, it will emit a specific photon, E equals HF. So a specific frequency. Energy of a specific wavelength in the visible range, because the frequency can be replaced by C over lambda. So you can see how that corresponds to a difference between these energy levels. So now I've put the 6 parts in blue. I've clarified it when I was speaking through it on the first run through of this video. And the quality of your written communication, is it clear what you're trying to say? Are you using the correct terminology? And have you made a logical connection between the points that you've made? Have you reasoned it well? Basically, if you got any of these 6 points, you're guaranteed 4 marks, even if it's not crystal clear, but these will get you up to 4. The other 2 marks are based on the judgment of the examiner, whether you've made a good logical reasoning between the points. Okay, so it's connecting all your thinking. Okay, so once again I repeat that the whole point of these exam questions is to show how you can improve the clarity of your communication. I'm going back to the wrong question. So question 16, second part, is now showing on the screen. So it is also possible to make atoms in a sample of air emit visible light. So it's the same concept with the hydrogen. They want you to now explain the next part. Explain why it says the light emitted by air has a large number of different wavelengths compared to hydrogen, they mean. That wasn't H2, it was H atoms. So the more simple the atom, the fewer energy transition are possible. Okay? The more complicated the atom or the molecule, which is even more complicated, the more variation in energy levels you have, and therefore you will be able to get more transitions possible. Air contains a mixture of different gases, molecules. So as long as you explain that it has a different mixture, there's already 1 mark out of the 2. Each type of gas or molecule has its own combination of energy levels or transitions, and that's why you would get more, so a greater. So this is driving the point home. This is what I'm saying to my students. Don't just stop there. That's a ... You can leave it to be implicit. But what if the examiner is looking for a keyword that's in the second part of this answer? So a greater variety of photon energies is possible, corresponding to different wavelengths and different transitions from the different energy levels. So you can see how much you can go deeper into the answer. And students who go deeper into their answer, obviously under the pressures of the exam timing, will get the highest marks. Okay, that's the 8 marks for this question. Okay, the next question is a core practical. It's the final core practical in year 12, which is core practical 8, and it's to do with the internal resistance of a cell. So here you've got an EMF of a cell. I've drawn it looking like a battery with the positive end of the battery shown with this positive end sticking out. They've drawn it with a dotted line going round, and they're saying the EMF is E, epsilon is the symbol we use for EMF, connected in series with a variable resistor. Here's the variable resistor, which has a value of R, as shown. The internal resistance of the cell is little r. Okay, I'm going to rewrite that again. So the voltage that's inside the cell, the current obviously goes inside the cell too, is equal to IR. Now this amount of voltage is lost volts. We call it lost volts because it's no longer available outside the circuit. So you automatically, when you're running a circuit and current is flowing, the current goes through all parts of the circuit, including going through the cell itself. And obviously some of the current is going through the internal resistance, so that means you will lose it from your maximum value. They then tell you that when R is 12 ohms, the reading on the ammeter is 107 milliamps. The circuit is switched on for 300 seconds. In this time, 50 joules of energy is transferred. So we know the energy transferred is in joules, and it's equal to the voltage that you're using at that value, the current, 107 milliamps, and the time that it's referring to. So this will give us a value corresponding to what they want us to work out. So they're saying this is what's happening. Now obviously that's the total voltage, because that's the energy that is transferred by the cell in total. So the total energy is then allows you to work out the voltage at that that's causing it. So that's going to be the EMF of the cell. So you divide that and you come up with 1.56 volts. So that's how they work out the EMF of the cell in question 17. Okay, so as long as you've done that, you will get this corresponds to the maximum. Now the sum of the EMFs is 1.56 volts, which is given out by the battery. Some of it is lost inside. So it doesn't say where the energy is going. It just says that's the total energy that's transferred. So we know this V is actually the EMF. Okay, so we know that the EMF that's supplied, the energy supplied by the cell, is equal to the sum of the potential differences in the circuit. So you could, this is one of the potential differences across the external, and the sum of one of the potential differences is the lost volts inside the cell. So you could rewrite that. This is Kirchhoff's second law, as being the sum of the PDs is equal to the current times the resistance outside and the current times the resistance inside the cell. Okay? So you then say, well, this is 1.56 volts is equal to the current which we know is 107 milliamps, is equal to the external resistance plus the internal resistance. So now you put the values in, we know the external resistance, we know the current, and we know the EMF that we calculated based on the information they gave us about the energy supply, and the only unknown is little r. You put it in the equation, change it all around, you'll get 2.58 ohms as your answer. And the ticks show you where you get your marks for. That's a 5-mark question. And remember, it's a core practical, so you need to know how to do this as an investigation. This is a quick way of working it out. They also expect you to know how to do it graphically. Okay? So y equals mx plus c is a major part of the core practicals that you need to know. What variation, what independent variable we have, what dependent variable we have, and that's going into it in part C. In part B, first of all, it says increasing R, the external resistance that we just looked at, would make the terminal potential difference closer to the value of the EMF that we calculated. Explain why, without further calculation, this would happen. Okay, so if you have a bigger resistor, a bigger resistance externally, the current will drop. And if the current drops, you'll have less voltage lost. Okay, so if the resistance increases, the current decreases in the circuit, and therefore the amount going through this resistor R will also be less. So the lost volts, if you remember, is equal to the current in the circuit times the little value. So not the lost volts will also be less in the circuit internally. So you'll have more of your EMF remaining, because the terminal potential difference is how much you measure across the cell, which will be the same as how much you're measuring. And if you've got lost volts there, this value is smaller, so V will be getting closer to the EMF. And now it's going into the final part of the question, which is to analyze how you do this as a core practical. So explain, so voltmeter is added here, you can put it also where I put it, to determine the value of the internal resistance using a graphical method, which is what I told you need to use. So you need to get to the point where you can explain it as a y equals mx plus c variation. So you vary R externally with the variable resistor. Using the variable resistor, you vary the R in the circuit. Record corresponding readings of voltage and current. So these are your two variables that you're measuring. Okay? So you'd vary R to be able to get a different terminal potential difference, TPD, and that will cause a different current to flow. Okay, plot a graph of V against I. So here's your V on the graph, and here's your I on the graph. And the gradient should give you a value of minus R, internal resistance. So if you recognize this by having studied the core practical 8 properly, they will give you your 4 marks. Of course, then, if they ask you a bit more detail, the intercept on this axis will be the maximum voltage, because you can see the voltage drops as the current increases. Okay? Now, why does that happen? Well, EMF equals Kirchhoff's second law, IR plus IR. So this is the terminal potential difference, which is the value across R. So you could replace that with E equals the reading, the voltage that we're varying, and the internal resistance there. So V, if you change the subject of the formula around, you can make V the subject of the formula because that's on the y-axis. We want the y-axis on the left-hand side. That would be EMF minus IR. So the I is on the x-axis, and R is the gradient. Okay, and that minus shows that the gradient is negative. And obviously the intercept is E, the EMF. So this is the level that you've got to reach for Unit 3. So this is the kind of stuff, that's why they make you do the core practicals. Whenever they have it, they want you to show what did you put on the y-axis, what did you put on the x-axis, and what does that imply about the gradient and the intercept. Okay, if you can do that for all the core practicals, you are ready for Unit 3. Okay, so Unit 3 does not require any more content. It's the same content. It's just the skills of the practical. Okay, so now question 18, the final question. The satellite ICE-SAT-2 is a satellite launched into space by NASA, blah, blah, blah. Our purpose of the satellite is to measure the thickness of ice on the Earth's surface. Okay, the satellite is powered by using solar panels, and a laser in the satellite produces a beam of photons. which travel to the Earth and back. So it goes there and back. So the distance is twice. So you have to remember to use the there and back rule for the distance. Okay. If you're calculating the time. Calculate the intensity of solar radiation. So the intensity of solar radiation is given by this equation. Intensity is the power divided by the surface area of the sphere that it reaches. So calculate the intensity of solar radiation using this equation. This is given to you on the equation sheet as it reaches the satellite. They've given you the distance from the sun to the satellite. Okay, so solar radiation means from the sun. The distance is equal to the distance of the Earth to the sun, because obviously it's in orbit around the Earth. So it's on a scale that we're only measuring accurately to 3 significant figures. So I think the average is 1.48. So this is just a general ballpark figure for the distance to the sun. So it's given to you in meters already. And the power of the sun is how much power is giving out at its surface. So at the surface of the sun, this is how much power is radiating. So it's 3.83 times 10 to the 26 joules times 10 to the 26 joules per second. So if you think of that, compare it to the equator. I always tell students, I think the intensity is about 1,300 approximately per square meter at the equator on a sunny day with the sun overhead. So here we want to work out the area of the sphere as you get further away. So that's the distance r. As you get a distance r, the sphere that is now spread out, instead of being at the surface of the sun, it's now a much larger sphere of 1.5 times 10 to the 11 radius. So as you double the distance, each time you double the distance, the area becomes 4 times as large, because it's proportional to r squared. So if you want to work out the area of the sphere, the surface area of the sphere, you put that in, you'll get the answers. They didn't do that in the calculation, but if you divide the power of the sun by 4 pi r squared, so you put the values in the calculator, you'll get 1,355, which would, depending on how accurately we've calculated it, you have to round it up to 3 significant figures. Yeah, because that's the maximum you should give. You shouldn't give it to 4 significant figures. I make that if it's 1,355. I didn't do the calculation myself. This is what the examiners have put. But they rounded it down to 1,350. So I'm assuming that value, that fourth value, is maybe slightly less than 5. It might be 4.9 or something. So you could try that yourself if you want to make sure. It then says the laser light emits the wavelength of lambda of 532 nanometers. Okay, so you need to know that that's 10 to the minus 9. Okay, there's a 10 to the minus 9. Calculate the energy in joules. Well, energy in joules for a photon is E equals hf, and hf can be represented by c over lambda instead of the f, so you can put it directly in there because you know c, you know lambda is given to you, and h is given to you on the data sheet. So here's h, here's c, here's lambda. I did it all in one go. If you do that, you'll get energy of 3.74 times 10 to the minus 19 joules. So they could ask you to convert them to electron volts in another exam. So would you know how to do that? Okay, think about it. We did it before the other way around. So you have to be able to convert units from electron volts to joules, and you probably need to obviously do it in the reverse direction as well. Okay, this is now the last page of the exam. So it says that photons released by the laser are directed towards the Earth. The mean time, yeah, when it says mean, they mean, don't use average, because average could be mode or median. So they usually mean average means the mean average, not the mode or the median. So the mean time for the photons to return to the satellite is 3.20 milliseconds. That means it's 1.60 milliseconds to go there and 1.60 milliseconds to go back. So don't get confused with that. You do need to divide the time by 2. Okay? So calculate the height. Well, the height is the distance. The time to go to Earth is half of the time to go there and back. So you divide it by 2. And if you do it correctly, you'll get 4.8 times 10 to the 5. You can quote that as kilometers or meters for your 2 marks. Finally, it says when the photons arriving at the satellite are detected, only those with the wavelength of exactly 532 nanometers are used in the analysis of the results. Suggest why? Well, they just want to see that you can think. Well, photons from other sources may also arrive at the satellite. So the detector, depending on how it's set up, could be detecting light of other sources as well. So you only want photons emitted by the laser to be recorded. Yes, you want to be analyzed, okay? So this is what we should be analyzing, because it's basically the light we sent has come back to us. So this is the important information, and you'll get 1 mark if you express it clearly. And then it says, part D, at one point, the satellite passes over a flat sheet of ice. The sheet is 1,000 meters above sea level. Explain how. So it's another explain question. So it means you have to drive the point home and explain it as deeply as you can. The measurements are taken. Explain how the measurements taken by the satellite can be used to show that the ice sheet has a flat surface, and secondly, is higher than sea level. So that's the 2 marks. 1 for the showing how you can explain that it's a flat surface, and 1 mark for explaining that it's higher than sea level. Okay, so if it's at a flat surface, all measurements taken across its area should take the same time as you're scanning the full area. Yeah, so if you go from one end to the other, because it's flat, the time taken should be identical from the beginning of the flat sheet to the end and in the middle as well. Okay, so and then secondly, how do you know it's higher than sea level? If it's higher than sea level, the time recorded should be less to go there and back from the laser, etc., compared to something at sea level. Okay, so that's assuming they knew the time it takes to go from sea level. Okay, so that's how you get the final mark. So thank you very much for listening to the second part. It's I hope you found it useful going through the details, the concepts, the mathematics, and the application of the concepts to the latter part of the questions in the second half of the question, the second part of the paper, section B. So section B is 70 marks, and we had 10 marks from the multiple choice, which adds up to 80. So if you found it useful, please share it and with your friends if they're doing the same exam as you. We do want to get as many subscribers as possible, so if you want to share this with your friends, that will help us a lot. And if we get enough subscribers, we'll continue to offer this service in future years. So if you're in year 12 now, then we'll continue to do it in year 13 as well for you. So that's it. Hopefully see you in the next video, and thank you for listening. Bye for now.